Welcome to lecture number 5. We are entering into the second unit, that is thin wire antenna. That we are going to discuss in this lecture. We are going to discuss retarded potentials and radiation from small electric to dipoles. So first of all, what is meant by this potentials, or what is meant by this retarded potentials? Okay, we are having two potentials. One is scalar potential, that is represented with V, and the other one is vector potential, it is represented with E. So what is the difference between general potentials and retarded potentials? What is the need of that retarded potentials? What is the need of that retarded potentials? Okay, we will discuss in this lecture. Okay, we'll discuss in this lecture. So see here, so potential functions and electromagnetic fields. Okay, so see here in the state of electrostatic fields, in the case of electrostatic fields or steady magnetic fields, the electrical fields or magnetic fields can be easily obtained by first setting the potentials in terms of charges or currents. Charges or currents. Okay, either in the case of electrostatics or in the case of magnetics. But electromagnetic combination of both electric and magnetic fields, the similar process. First, the potentials are obtained in terms of charges or currents, and the electric and magnetic fields are obtained from these potentials. Okay, so for obtaining the potentials for electromagnetic fields, there are two approaches. So there are two approaches to obtain the potentials from the electromagnetic fields. The first approach is heuristic approach. The first approach is heuristic approach, and the second one is Maxwell's. Okay. In the first approach, using trial and error, the potentials for electric and magnetic fields are generated. Okay. This is shown that potential satisfy the Maxwell's equation. This approach is called as heuristic approach. So the second approach is the Maxwell's equation. So in order to get retarded potentials, there are two approaches. One is heuristic approach. The other one is Maxwell's equation approach. Maxwell's equation approach. Okay, so these are two types of retarded methods, approaches to obtain the retarded potential. Okay, let us discuss the first one, that is heuristic approach. Okay, so let us discuss, this is the heuristic approach. So see here, for the heuristic approach, in electromagnetic case, we have seen that line charge density, surface charge density, volume charge density. So it is represented with dq is equal to rho L into dl, line charge density. Okay, so rho S is surface charge density, rho V is volume charge density. So dq is equal to, if it is surface, the formula for dq is equal to rho S into ds. For volume, it is dq is equal to. So from this, what is the value of q? Q is nothing but integral of rho L dl. Here Q is nothing but integral of rho S ds. Okay, so here Q is nothing but integral of rho V d. So we know that the scalar potential, the expression for scalar potential V, the expression for scalar potential V is equal to Q by 4 pi epsilon. For example, let us take for surface charge density. Okay, so in the place of Q, I will replace this with formula. Okay, so Q is equal to integral of rho V into d. Integral of 1 by 4 pi epsilon into integral of rho VR to dV by. Okay, so for similarly for this is for electrostatics. Okay, so similarly for magnetostatics. Okay, in magnetostatics we discuss in terms of current. Okay, so line current is represented with IDL, surface current is represented with KDL, and volume current is represented with JD. Okay, so line current with IDL, surface current with KDS, volume current with JD. Okay, so now let us consider a surface charge density Now let us consider the surface charge density. Let us consider the surface charge density dV dash. So it is at a distance of r dash from the origin. Let us consider this is origin. Let us consider this is origin. It is at a distance of r dash. It is at a distance of r dash from the origin. Point P is the point of observation. Point P is the point of observation. Okay, so let us consider a volume charge density dV dash, which is at a distance of r dash from the origin, as shown in the figure. The scalar potential point P, point of observation, the scalar potential at point P due to this volume charge density is given as, due to this, the volume charge density is given as V of r dash is equal to 1 by 4 pi epsilon into rho V of r dash into dV dash by r. This is expression. Okay. So similarly, this is for volume charge density. Okay. So similarly, for study of magnetic field in a homogeneous medium, the vector potential, the vector magnetic potential, the vector magnetic potential can be expressed as, similarly, let us take this. Okay, so here for volume charge current, it is represented with J. Okay, so for magnetostatics. Okay, let us consider the same thing here. Let us consider. So this is J. This is point of observation P. This is origin. So it is also at a distance of r dash from the origin. This is r. Okay. So the vector magnetic potential due to this current element. Okay. So it is represented with A of r dash is equal to, this is A stands for vector magnetic potential. This one stands for scalar potential. Okay. So it is equal to mu by 4 pi into integration of J of r dash into dV dash by r. Okay, so these are all the formulas we have studied in electromagnetic. So, okay, so this is the formula. Volume current, it is represented with J. Volume current is represented with J. Okay, so next, but the charge and current, the charge and current, the charge and current distribution producing the electromagnetic fields vary with respect to time. Then we must modify the potentials. Then we must modify the above potentials. Then we must modify the above potentials. Modify the above potentials as, since they are varying with respect to time. So initially we have simply write it as V of r dash or A of r dash. Since they are varying with respect to time, I am going to write it as V of r dash into t is equal to 1 by 4 pi epsilon integral of rho V of r dash comma t by r into dv dash. Okay, so similarly, A of r dash comma t is equal to 1 by 4 pi epsilon into integration of J of r dash comma t by r into dv. So here we have introduced the time. Okay, so the velocity of the electromagnetic field, the velocity of electromagnetic field through any homogeneous medium, can be described in terms of mu and d. Okay, permittivity and permittivity. permeability. Okay, so it is given as velocity is equal to 1 by root of mu into epsilon. Okay, 1 by. Okay, so then the potentials at any point is not due to, then the potential set any point is not due to the value of charge density at the same point at the same instance, but its value at some previous instant. But its value is at some previous instant as the electromagnetic wave propagate with the finite velocity. Okay, so it depends upon the not only the present time but also it depends upon the previous instant. So therefore, P of r comma t is equal to 1 by 4 pi epsilon to OV of r dash into t minus r by b. Okay, by r into t. Similarly, a of r comma t is equal to mu by 4 pi into integration of j of r dash comma t minus r by v by r into dv dash. Okay, so this is a t minus retarded. The potential is getting reduced by r by v. Okay, so that is nothing but retarded potential. This above two equations. This above two equations. This above two equations are called as retarded potentials. These above two equations are called as retarded potentials. Okay, so this is the first approach. Okay, so this is the first approach. What we call this approach? This approach is called as heuristic approach. Okay. So similarly, the retarded potentials. What are the two techniques? One is heuristic approach. The other one is Maxwell's equation approach. The other one is Maxwell's equation approach. Okay, so let us go to the second method. Let us go to the second method, that is Maxwell's equation approach. That is Maxwell's equation approach. So, Maxwell's equation is, first of all, we'll go for Maxwell's equation approach. We'll go for Maxwell's. So, for Maxwell's equation approach, in order to get retarded potential, okay, first of all, we should have the knowledge regarding Maxwell's equation. So we are having different Maxwell's equations, four Maxwell's equations are there. Example, delta C is equal to minus 2p by 2p. We know that with the relation B is equal to H. The same thing I can write it as 2 H by 2. Let's consider this expression. So similarly, second one, delta H is equal to J plus dou D by dou T. We know that D is equal to epsilon E. D is equal to epsilon E. B is equal to mu H. So this can be written as J plus epsilon into dou D by dou T. Let us consider this as equation 2. Okay, so that is third equation. Delta T is equal to 2V. This can be written as D is equal to epsilon. So therefore, this the same thing can be written as epsilon into delta T is equal to 2V. This can be written as delta T is equal to ρV by epsilon. This is considered as equation 3. Let us come to the fourth equation, delta T. Curl of magnetic divergence of magnetic field is 0. Or we know that B is equal to mu H. The same thing can be written as del dot H is equal to. So these are four standard Maxwell's equations. Okay. So this is the first one. This is the first expression. Del plus E is equal to minus mu into dou H by D. This is the second equation. Del cross H is equal to J plus epsilon dou E by dou D. And the third equation, delta T is equal to V or delta T is equal to dou rho v by epsilon. So rho v by epsilon. Rho v by epsilon. This is the third one. And fourth one, delta t is equal to 0, delta dot h is equal to 0. This is fourth one. Okay, so this is fourth one. Okay, so let us take from an equation one. This is my equation one. Okay, let us consider the equation one. So what is the equation one? The equation one is del cross E is equal to minus mu into rho h by 2. Okay. So you know that what is the relationship between magnetic field and vector potential A? So there is a relation V is equal to, you know that V is equal to del cross. So what is the relation between V and H? V is equal to mu H. Mu H is equal to del cross A. Therefore, what is the value of H? H is equal to del cross A by, so here A is vector potential, B is magnetic. Okay, so B is equal to mu. Okay, magnetic field, magnetic flux density. Okay, so A is vector potential. Okay, so H, what is the value of H? H is equal to the value of H is equal to value of H is equal to del cross A by B. The value of H is equal to del cross A by B. The value of H is equal to del. So in the place of H, simply substitute that. So del cross E is equal to minus mu by dou D of del cross A by you may get cancelled. So therefore del cross E is equal to minus 2 by 2 P of del cross A. Okay. I'm interchanging the operators. Interchanging the operators. Operators will get del cross E is equal to minus 2 into A by. Okay, so I'm bringing this side del cross E plus 2 into A by 2 is equal to 0. Therefore, I'm taking row comma. So it is equal to E plus 2A by 4T to 0. So this is the expression. From the vector identity, from the vector identity, curl of gradient of a scalar. This is curl. Okay, curl of gradient of a scalar is 0. Okay, so it is clear that upon this it is clear that E plus dou A by dou T is equal to minus 10. E plus dou A by dou T is equal to minus 10. So it is clear that curl of gradient of a scalar. Okay, so this scalar is 0. So E plus dou A by dou T is equal to 0. From this E is equal to minus 10P minus dou A by dou T. E is equal to minus 10B minus 2A by 2. Okay. So we know that mu H is equal to del cross A. Okay. So therefore, from equation 2, what is the expression equation 2? This is my equation 2. Okay. So from equation 2, from expression 2, from equation 2, that is, what is that? Del cross H is equal to sigma plus epsilon into 2E by 2T. Okay, so that is del cross, what is the value of H? Del cross A by mu. So it is del cross A by is equal to J plus epsilon into 2 by 2T. What is the value of E? E is equal to this one, minus 2V into minus 2V minus 2A by 2. Okay, so it is, we know the formula of vector potential, that is del cross of del cross A is equal to the expression for it is del log del dot A minus del square. So the above equation is also in this form. Okay, so del cross of A is equal to this one. Okay, so I can write this expression. This can be written as del log del dot A minus del square A is equal to, here mu is there. Here mu is there, simply move this side. Okay, so you get mu J minus mu epsilon into del square A by 2 square minus mu epsilon to rho by 2 of del. Okay, so therefore del square A minus rho of del dot A is equal to minus mu J plus mu epsilon into del square A by 2 square plus epsilon into rho by 2 of del. So let us consider this expression as C. Let's consider this as expression C. Okay. Now let us consider the equation. What is my equation? This is my equation 3. Okay, this is my equation 3. So from equation 3, from Maxwell's equation 3, what is that equation 3? Del dot E is equal to rho V by epsilon. Okay, so what is the value of E? The value of E is this one. So let us consider this as A. The value of E is this one. Okay, so value of E is this one. So simply substitute here. Del dot. What is the value of E? Minus rho V minus rho A by rho T is equal to rho V by epsilon. So this simply multiply that minus del square A minus rho by 2 of del dot A is equal to rho V by epsilon. Okay, so from this del square V plus rho by 2 of del dot A is equal to minus rho V by epsilon. So let us consider this is okay. So this is expression C. This is expression B. Okay, so you know that Helmholtz equation. What is the Helmholtz equation? Says that Helmholtz equation. What does it says that? Very, very important one. Any vector field can be defined. Any vector field can be defined uniquely if curl and divergence, curl and divergence of the field are known at any point. This is very, very important one. We have studied in EMTL. Helmholtz equation says that any vector field can be defined uniquely if curl and divergence of the field are known at any point. Okay, so means that is del dot A. This is vector. Any vector field can be defined independently if curl and divergence of the fields are known. So it is minus mu epsilon into rho V by rho T. Okay, so this is very important equation. Let us consider this is expression is. Okay, so this is Lorentz gauge condition. Gauge condition for potential. For potentials. Okay, so del dot A. So this gives the relationship between scalar. This is my scalar. This is my vector potential. This is my scalar potential. This Lorentz wave condition gives the relationship between both vector potential and scalar potential. So if you observe here, okay, so in equation C, we are having delta T. Okay, so in equation 4 also we are having delta T. To get simplify this, the place of delta T, we want to replace the Lorentz gauge condition. Okay, Lorentz gauge condition. So simply substituting the equation E in C. Here we are having delta T. Here also we are having delta T. Okay, so let us substitute equation E in C and D. Okay, C and D. Let us substitute in equation C. First, what is the equation C? This is my equation C. In delta T, I will simply substitute this Lorentz gauge condition. So here it is del square A plus rho of minus of minus here. Already minus is there. Okay, minus of minus will become plus. Okay, minus plus mu epsilon into 2v by 2t is equal to minus mu j plus mu epsilon into 2 square a by 2t square plus mu epsilon into 2 by 2tr. Okay, so therefore this expression. So this one and this one will get cancelled. Okay, so therefore this expression becomes del square A is equal to minus mu j plus mu epsilon into 2 square A by 2 square. Okay, so let us consider this expression is F. This expression is F. Similarly, substitute the equation in E in T. Okay, so this is my T. This is my T expression. In the place of delta T, simply substitute Lorentz gauge condition. So simply substituting E in T. Okay, so therefore we get del square P plus rho by 2tr minus mu epsilon rho v by 2t is equal to minus rho v by epsilon. So therefore del square V minus mu epsilon del square V by 2t square is equal to okay. Let us consider this expression as G. Okay, so we have got expressions F1 G. Okay, so both the equation F, this is equation F, this is the second order differential equation, and this G is also second order differential equation. So the solution for second order differential equation, second order differential equations F1 G is given as so A of R comma B vector differential is equal to mu by 4 to J of R dash of T minus R by B to R dV dash. Similarly, V of R comma T is equal to 1 by 4 by epsilon of rho V of R dash into T minus R by V by R into dV dash. Okay, so these are called as vector functions. Okay, so these are called as retarded vector functions. Retarded vector functions. Okay, so this is how we will get retarded vector potentials by using heuristic approach and Maxwell's approach. Okay, so these are two potentials retarded potentials by using heuristic approach. This is by using Maxwell's equation approach. These two equations are Maxwell's equation approach. Okay, so now let us go to the next topic. So now we have obtained the vector potential potential. Okay, means A is obtained. Okay, so vector potential potential is obtained. For example, this is vector potential potential A. So, what is the procedure? What is the procedure you want to do for calculating fields? Okay, so for example, take any current element. To take any current element at point P. At point P, how to calculate the electrical field and magnetic field. How to calculate the electrical field and magnetical field at any point P. So what is the known thing? We know the vector potential. Okay. So how to calculate electrical field and magnetical field at that point P, which is, this is the current element. Due to this current element or any element, okay, any, it may be dipole or it may be any current antenna is there. Okay, so at point P is there. How to calculate the electrical field and magnetical field if you know the retarded potential, that is vector, scalar, this A stands for vector retarded potential A. So if you know A, how to calculate electrical field and magnetical field at a E. So the simple step is the first step. This step is what out this step. Okay, so how to calculate if you know A, if we know these steps are very, very important. If you know vector potential A, vector retorted potential A, how to calculate electrical field and magnetical field. How to calculate electrical field and magnetical field. E and H, how to calculate at a point P. Okay, so the first step is very, very important. The first step is if we know A, we know that the magnetical field B is equal to, what is the relationship between B and electrical vector potential? B is equal to del cross A. Okay, so what is the relationship? B is equal to, you know that B is equal to mu H. Therefore, B is equal to mu H is equal to del cross. So from this, how will you get the H? H is equal to 1 by mu of simple cross product of E. So this is how we can obtain the magnetic field. This is how we can obtain the magnetic field. Field at point P. Okay. Okay. Now, once if magnetical field is known, now H is available. Now H is available. But the other thing you want to calculate, you want to calculate the electrical field. How to calculate the electrical field? Hmm. How to calculate the electrical field? The electrical field is, we know that. So, what is the Maxwell's equation? Del cross H is equal to J plus epsilon to dou E by dou E. Okay, so what is the value of J? J, it is sigma E plus epsilon to dou E by dou D. Okay, for free space, sigma is equal to 0. Therefore, del cross H is equal to epsilon into dou E by dou D. Okay, so from this, what is the value of dou E by dou D? Dou E by dou D is equal to 1 by epsilon into del cross H. Okay, from this, what is the expression for E? Is equal to 1 by epsilon into integration of del cross H into D. This is how. So this is the procedure. This is the procedure you want to keep in mind. Okay, so this is the standard things for calculating any electrical field or magnetical field for any current element at point P. Okay, so the known thing is you know the vector potential A. Okay, if you know the vector potential A, how to calculate? How to calculate the electrical field and magnetic. So once if we know the vector potential A, okay, so we know that B is equal to del cross A and we know that B is equal to mu H. So how will obtain the H? H is equal to 1 by mu into del cross. So now we have got magnetic field. Once you got the magnetical field, how to calculate the electric field? Okay, so there is a, from the Maxwell's equation, del cross H is equal to J plus epsilon. You know that J is equal to sigma A, but P plus sigma is equal to 0. Therefore, del cross H is equal to epsilon into dou E by dou T. From this, dou E by dou T is equal to 1 by epsilon into del cross H. Therefore, E is equal to 1 by epsilon into integration of del cross H into. So, this is the procedure you want to keep in mind. This is the procedure you want to keep in mind for calculating electrical field and magnetical field at any point P. We have retarded potentials. If you know the retarded potentials. If you know the retarded potentials. Okay. Now let us go for the next thing. Radiation from alternating current. Radiation from alternating current. Okay.